Okay, so in this video we will calculate the force Q as shown here in order to cause a total deformation of 0. We will do this by using this equation shown here. Okay, so the problem reads, determine the force Q such that the deflection or deformation of A is 0. The system below is made of aluminum for which the modulus of elasticity is equal to 270. So what it means by deformation of 0 is that this point will not experience any deformation. So that means that this point will not be compressed or stretched. So the first thing that we will want to do is to divide this system into two segments. And it is two segments because there is a change in area. So this will be segment 1 and this will be segment 2. So we will start off by doing segment 1. So we will draw out an image to know what forces will be applied. So this is fixed and we have to calculate the support reactions. So to do that, we will put the 4 kilonewtons going in this direction to oppose this force here, and as well as a Q force here to oppose this Q here. And we know that at point B, there is a force Q here, but then we won't need that because the force that we will use in the equation is the force applied at the cut. So it will be this force here. We have to calculate this force. So to calculate this force, let's call it force BC. We will do the sum of the forces and set it equal to 0. And we will identify going up as positive and going down as negative. So then we will put force BC minus the force of 4, which is going in the down as shown here, plus the Q, and set that equal to 0, and we get that the force BC is equal to 4 minus Q, and this will be in kilonewtons. So we will use this force to calculate the deformation of this segment. So the equation that we will be using is this equation, which is the deformation is equal to the force times the length over the area times the modulus of elasticity. So we will plug in the numbers that we know to solve for this. So the deformation of the segment BC is equal to the force, which the force is the force applied at the cut. So that will be the force BC. So we will put 4 minus Q. And then to convert to the proper units, we will do times 10 to the 3. Then multiply that by the length, which is the 0.5 meters as shown here, over the area, which will, since we are given the diameter, we will do the pi diameter divided by 2 squared. So then it will be pi 60, then the unit conversion, so 10 times negative 3, 10 to the negative 3 power over 2 squared times the modulus of elasticity, which is 70 times 10 to the 9th for unit conversion. So we will be using this to solve for the problem. We can now move on to calculate for the second part. So we will once again draw out an image of the system so that we can put the forces and identify which forces and what length to use. So this is B, this is A. We have a force of 4 kilonewtons at A, and at B we have the Q. And we know from the previous one we have to take a look that force FB is pointing up, so then we will have the opposing force FB in the negative direction, which is a 4 minus Q. But then we won't actually be using this 4 because we will use a force at the cut, so we have to find this force right here, which is at the cut, which we'll call force AB. So in order to solve for force AB, we'll do the same that we did to calculate the force BC. So we will sum the forces and set it equal to 0. So then we will identify that up is positive and down is negative. So then it will be force AB minus the 4 minus Q, which is here, minus the Q, and set it equal to 0. So then we simplify it and we get we see that we can cancel out the Q, and we get that force AB is equal to 4 kilonewtons. So then we can go ahead and substitute it into the equation that we use in part 1 as well. And we get that the deformation in part AB is equal to the force, which is the force at the cut, so it will be the 4 times the 10 to the 3 for unit conversion, times the length, which is 0.4 meters, which is here, over the area, which is the pi, the diameter cut in half, so it'll be 20 times 10 to the negative 3 for unit conversions, over 2, squared times the modulus of elasticity, which is 70 times 10 to the 9. And we will also use this to solve for the problem. So since we want a deformation of 0, that means that the deformation at A, which is this point, is equal to 0, which is the same as the deformation of BC plus the deformation of AB being equal to 0. So if you substitute these values in that we just solved for into this equation and simplify it a little bit, we get 7.28 times 10 to the negative 5 plus 2.526369 times 10 to the negative 9 times 4 minus q is equal to 0. And if you solve for q, you get 28,820.1 newtons. So that is the force q that will allow there to be a deformation of 0 for this system. So some steps to keep in mind when solving these types of problems is to first make sure that you divide the system into segments depending on if there is a change in area or if there is different forces applied at different points. So that's when you want to split it into segments. So I hope this video was helpful and thank you.